Alright, in this one we're going to talk about Turing machines. This will be a basic and quick introduction to Turing machines. So as you might not be surprised to hear, a Turing machine is a 7-tuple. So a Turing machine is a 7-tuple, and that's just kind of a long-winded way of saying it's got 7 parts. So the first part is Q, which is the finite set of states. This should sound familiar, because every model we've looked at so far has a finite set of states. The other thing it has is an input alphabet, sigma. And just like before, the input alphabet is finite. However, we're going to make a special rule about the input alphabet, and we're going to say the input alphabet does not contain the blank symbol. The blank symbol is a symbol that appears on the tape when the Turing machine begins. And we're going to say that the blank symbol cannot be part of the input. So the blank symbol looks like this. Oops, that's kind of confusing. But this little guy right here is the blank symbol. So we're going to say that our input alphabet cannot contain the blank symbol. And then we're going to have another thing called the tape alphabet, and we're going to represent that using gamma. And the gamma contains the blank symbol, but gamma also contains the input alphabet as a subset. So this is the tape alphabet. And the blank symbol is an element of the tape alphabet, and sigma is a subset of, but can't be equal to, the tape alphabet. So if you think about it, sigma cannot be equal to the tape alphabet because the blank symbol has to be in the tape alphabet, and the blank symbol cannot be in the input alphabet, so this has to be a subset of that, because gamma contains at least one symbol that sigma does not contain. Okay, when you're learning a new model of computation, there's 2 things you want to pay attention to. The first one is how do you make a transition. The second one is what does it mean to accept. Everything else is pretty vanilla between the different models. Except for with the Turing machine, there's a little bit of subtlety with sigma and gamma, but I don't think you're going to get blown away by that. So the transition relation looks like this. So when you make a transition, you take a current state together with a letter from the tape alphabet, and then you go to the next state together with a letter from the tape alphabet, and then you either move left or you move right. So what the transition function describes is that you start off in some state and you're looking at some letter on the tape of the Turing machine, and then you take a transition to another state, and then you write this letter. So you write this letter over the top of the letter that you saw as input, and then the final thing you do is you move the tape head. So this is a significant feature of the Turing machine. So if you remember, a deterministic finite automaton has no auxiliary memory. It just remembers what state it's in. A push-down automaton has a stack as its memory, so it can play around with the symbol at the top of the stack. The Turing machine, on the other hand, has a tape to represent its memory, and it can move around the tape, it can write things over the tape, it can go left, it can go right. So a Turing machine has a very general model of memory. It's essentially a sequential access memory, meaning that you can just access things sequentially in time. So it's like a VCR tape or an old cassette tape. You can access the contents of tape sequentially. In terms of performance, the fact that it's sequential access and not random access matters a little bit, but in terms of what problems we can and can't solve, the fact that it's sequential access versus random access is completely irrelevant. Okay, so that's 4 out of the 7. So the final 3 things are that it's got a start state. So it's got a Q0, which is a member of Q, which is the start state. The other thing it's got, which is maybe not too surprising, is an accepting state. So it has Q accept, which is a member of the states. So that's the accepting state. So we've got 1, 2, 3, 4, 5, 6. So the final thing we need is Q reject. So Q reject is a member of the states, and it's a special state that represents the fact that the machine rejected the input. In a deterministic finite automaton or a push-down automaton, we implicitly got rejection by saying that I'll tell you what the accept states are, and if it ends in any other state, then it rejected or didn't accept. But in a Turing machine, it's helpful to define a rejection state and an acceptance state. And so we do that right here. Okay, so that's the basic definition of a Turing machine. This is the 7th element. The thing I want to do now is draw a schematic diagram, well, like a block diagram of a Turing machine, and this will get you thinking about the configuration of a Turing machine. Okay, so a Turing machine has a little control thingy. That's basically what state it's in. It's got a tape. So the tape starts off with the contents. So this particular tape contains the words cat, followed by a bunch of blank symbols. And when we draw these things, what we usually would draw is a little arrow with a little line with an arrow on it. That would tell us what symbol we're looking at. And instead of just drawing a generic Q here, we'd want to pay attention to what state the thing starts off in. So this particular Turing machine is in a configuration where it's in state Q0, looking at the word cat, and the head is looking at the C right there. It's convenient to have a shorter way of expressing the configuration of a Turing machine, and so this is how we would write down the configuration of this machine. We'd write down C, Q0, A, T. So by convention, we're just going to write down the name of the state to the right of the letter that we're currently looking at. So since I'm looking at a C, I'm going to write down the name of the state to the right of that C, and this tells me that I'm looking at cat on the tape, I'm in state Q0, and I'm looking at the C because the state is written to the right of the letter I'm looking at. Something you need to catch is that there's two things going on here. There's something called the state of the Turing machine, and then there's something called the configuration of the Turing machine. So the state of the Turing machine is simply what state the Turing machine is in. It's a member of Q, in this case it's Q0. The configuration of a Turing machine is the tape contents, the head position, and the state. So a configuration contains three things. Okay, that's a very quick introduction to the mechanics of a Turing machine. Good luck.